Okay, show of hands. How many people know that RTD stands for Resistance Temperature Detector? I don't see too many. You should know it because I did use it in a previous video. Well, you know it now. RTD, Resistance Temperature Detector. The first RTDs consisted of coils of platinum wire wound around a ceramic core or a glass tube. And in order to protect the wires from damage, a glass, ceramic, or a metal sheath would cover these fragile windings. Today, thin film RTDs are made by depositing thin parallel layers of platinum onto a ceramic substrate. The length of the pattern determines the exact resistance that is needed for the sensor. Ever notice how many fun facts involve a lot of numbers? No different with RTDs. The typical temperature range is minus 200 degrees C to 800 degrees C. The European standard DIN or IEC 60751 specifies a resistance of 100 ohms at 0 degrees C and a temperature coefficient of resistance of 0.00385 ohms per ohm degree C between 0 and 100 degrees C. Now memorize that. Okay, relax. All it really means is you're supposed to get a perfectly straight line for your plot of temperature versus resistance. There are two types of specs for tolerances, Class A and Class B, both of which involve the equation shown in the slide that depend on temperature. It's a lot easier to remember them as Class A is the one with the 0.06 ohms of tolerance at 0 degrees C, and Class B has double that, or 0.12 ohms of tolerance at 0 degrees C. This chart looks more like a schematic for a roller coaster ride than a graph of sensor resistance versus temperature. We discussed the NTC thermistor in the last video. The less used PTC, or positive temperature coefficient thermistor, is the one with a positive but a curved slope upwards. The RTD looks like a plain old straight line with a positive slope. In reality, though, the curve is very linear, but not perfectly linear. You need to calibrate an RTD sensor if you want it to be perfectly linear. RTDs get used wherever a high accuracy temperature measurement is needed, as long as the data is somewhere within the range of minus 200 degrees C to plus 800 degrees C. They're popular in applications where people want to install the sensor, take the data, and not have to, or in the case of the space shuttle, not be able to access the sensor ever again. The excellent repeatability of RTDs appeals to the pharmaceutical industry. Measuring temperature in a gas or an airstream is another popular application. In that case, you will want the bare RTD element exposed to the gas in order to minimize the speed of response of the sensor. A hot wire anemometer is an RTD run in reverse. And now it's time to show you what commercial RTDs look like. You can buy them as a surface mount 0603 chip, just like this RTD from Vishay. And you can buy them as a sensor on a surface probe and bolt them to the object whose temperature you want to measure. This stainless steel probe is designed to screw into a thread hole in a tank or a furnace, and the pharmaceutical industry likes the sanitary sensors. They look like an explosion-proof head, but they're combined with the clean construction required for good manufacturing procedures. Let's recap. We discussed the accuracy, range, and typical applications for RTDs. Now we're going to use circuit diagrams to explain the core technology behind them, as well as how to linearize them, how to buy them, and how to integrate RTDs into a circuit.